Okay, so good evening everyone. Welcome you all to this fifth problem solving session for the NPTEL course Aircraft Propulsion. I am Anindo, a PhD candidate and a Prime Minister Research Fellow from IISc Bangalore, and we have been having this live problem solving session for last 4 weeks and related to the lecture content discussed in the NPTEL course Aircraft Propulsion. So in the last few weeks we have looked into the problems related to Brayton cycle, like ideal Brayton cycle, and then we introduce several non-idealities like the non-isentropic expansion and non-isentropic compression process, and looked into how we can compute the state points and different quantities of interest from by thermodynamic analysis like work output, heat input, thermal efficiency, work ratio, back work ratio, and similar stuff. And also we have looked at different Brayton cycle attachments in like reheater, heat exchanger, and intercooler, and looked into the effects of those in the net work output and the thermal efficiency when each one of them is used, and or when all of them are used together. Okay, so in today's week 5 lecture contents included discussion on real Brayton cycle, and how we include stagnation conditions or stagnation properties like stagnation temperature and stagnation pressure comes in while we do thermodynamic analysis of a real Brayton cycle, and other important considerations that come in when like solving numericals or analyzing a real Brayton cycle. Okay, so let's begin today's session. Okay, so this first problem is a derivation. This is based on the reheater attachment. So let's go through the problem. So in an ideal gas turbine cycle with reheat, air at state P1 and T1 is compressed to pressure RP P1 and then heated to T3. So here what this says that the final pressure after the end of at the exit of the compressor is RP P1, which means that RP is our pressure ratio here. There is then expanded in two stages, each turbine having a same pressure ratio, which we expect in a reheat cycle. So between the reheater, reheater is placed between two turbines, and the pressure ratio across two turbines is equal. And in the reheater, the working fluid is heated again to the first turbine inlet temperature in between the stages, which is what we call perfect reheating. If we assume the working fluid to be perfect gas with constant specific heat, and the compression and expansion are isentropic, we have to show that specific work output will be maximum when RP is given by this expression. So RP is the pressure ratio and beta is our temperature ratio, that is the maximum temperature to minimum temperature in the cycle. Okay, so let's begin. So first we will draw by drawing a TS diagram for the ideal reheat cycle. So this is an ideal reheat cycle. So first we have 1 to 2 is compression, 2 to 3 is heat addition process, then 3 to 4 is fast expansion, then 4 to 5 is again our reheating, and then 5 to 6 is our second stage of expansion, and 6 to 1 is our heat rejection process. Okay, so let's begin. So what first we can write, we know from the isentropic relation T2 by T1 is given by RP to the power gamma minus 1 by gamma, right? Okay, so let us, for the ease of it, let represent it as C for the time being. Okay, then we know another thing is the pressure ratio, it's in P3 by P4 is equal to P5 by P6. Okay, and so the pressure ratio across each turbine stage is equal, and we know that is generally equal to the square root of the total pressure ratio. The total pressure ratio is RP, so the pressure ratio across each turbine stage should be square root of RP. Okay, and and what is given here is one more thing is given, is that our T5 is equal to T3, which we get from this line, that this uh, air is expanded in two stages and each turbine has same pressure ratio, which is indicating by this: each turbine has same pressure ratio. Alright, and last sentence, and it is reheated to T3 between two stages, so T5 equals to T3. Okay, so let's proceed. Next we can write then T3 by T4, which is the temperature ratio across the first turbine stage, is equal to T5 by T6, which is the temperature ratio across the second turbine stage, and that is equal to the this is our pressure ratio across each turbine stage, that is square root of Rp to the power gamma minus 1 by gamma. Okay, so or we can write this as Rp to the power gamma minus 1 by gamma square root of entire thing, and this Rp to the power gamma minus 1 by gamma, for the sake of writing it in a short term version, we are representing it as C, that is square root of C. Okay, so next is our turbine work output. So we have to show that the maximum specific work output, when the specific work output will be maximum. So to compute the work output, we need to compute the turbine work output and compressor work input to get the net work output. So turbine work output, or you can write total turbine work output, because we have two turbines here, will be Cp times T3 minus T4, this is the, and plus Cp times T5 minus T6. Alright, okay, and since we know this is the temperature difference across each turbine is the same, that is usually the case for optimum work output and with perfect reheating. So we can just write this is 2 times Cp T3 minus T4. Okay, since each turbine work outputs are equal. Okay, so then we can write this is 2 Cp, if we take T3 common, this is 1 minus T4 by T3. So from there we can write this is turbine work output is 2 Cp T3 1 minus 1 by square root of C. Okay, so we are using this isentropic relation to get and putting it here. So T4 by T3 is basically 1 by square root of C. Okay, so we know the turbine work output now. So next we have compressor work input, this is Wc. So this is Cp times T2 minus T1. Okay, so again if we take Cp T1 common, we get T2 by T1 minus 1, and T2 by T1 is pressure ratio Rp whole to the power gamma minus 1 by gamma, which is C, right? So this is C minus 1. So now we know the compressor work input and turbine work output. So net work output is Wn, this is Wt minus Wc, which is 2 Cpt3 1 minus 1 by square root of C minus Cpt1 C minus 1. Okay, so now let's say we divide both sides by Cpt1, is a common way to normalize the net work output. We get 2 T3 by T1 1 minus by square root of C minus C minus 1. Alright, so now T3 by T1 is the ratio between the maximum and minimum temperature for the cycle, which we generally represent by beta. So this comes this will come as 2 beta times 1 minus 1 by square root of C minus C minus 1. Okay, this is our net work output normalized by CPT1. Okay, specific work output. Okay, now this will be maximum. We are invoking the calculus that this is the derivative of this entire thing with respect to, so here the independent variable is c, so c contains the pressure ratio, and c is like basically rp to the, c is rp to the power gamma minus gamma minus 1 by gamma, right, and gamma is constant, so basically c is proportional to rp, so we can write, if this is the case, when the derivative of the specific work output, net specific work output with respect to c is 0, then we will get max, this will be optimum. Okay, so now we take the derivative of this with respect to c, so dc of this is 2 beta 1 minus this was c to the power minus half, right, minus c minus 1. Okay, this is equal to 0, this should be 2 beta, okay, minus 1 into minus half, this should be into c to the power minus half minus 1, the first, sorry, this is the for the first term, then we have minus 1, okay, equal to 0. Okay, so this comes as out as 2 beta times half into c to the power minus 3 by 2 equals to 1. So this is beta c to the power minus 3 by 2 is equal to 1, or c is equal to beta to the power 2 by 3, right? Okay, c is equal to beta, so if we change side, we get c equals to beta to the power 2 by 3, and now c is rp to the power gamma minus 1 by gamma, so beta to the power 2 by 3. So now if we again rearrange, we will get beta is equal to 2 gamma by 3 gamma minus 1. Okay, this is what we wanted to find out, right? Okay, so it was given rp equal to beta to the power 2 gamma by 3 gamma minus 1, so this is what we get. Okay, so this is what we derived, is the what is the relationship between the pressure ratio of the cycle, or the compressor pressure ratio, to the temperature ratio across the cycle. The beta is our maximum to minimum temperature of the cycle, so this is a relationship for a reheat cycle when we want to have the optimum maximum specific work output. Okay, so this is one derivation that we did related to. Okay, so this is similar to what we did in case of just a simple ideal Brayton cycle, the condition for maximum work output, and in that case we find out the condition has to be the turbine exit temperature is equal to the compressor exit temperature. It turns out that, like, the relationship, and here the condition is rp should be equal to beta to the power 2 gamma divided by 3 gamma minus 1. Okay, so now let's move on to the some theoretical MCQ questions. Okay, so the question number 2, so we have, it says that consider the four following statements regarding real Brayton cycle. Okay, so we are talking about real Brayton cycle. So we have seen that real Brayton cycle has different considerations which we have to relax many of the assumptions that we make while solving for ideal Brayton cycle, like our expansion and compression processes will be non-isentropic. Apart from that, there will be pressure losses in the combustion chamber, reheater and heat exchanger, so we have to consider our pressure losses there. In addition, we cannot neglect the kinetic energy changes, so that kinetic energy change in kinetic energy we can account for by taking into account stagnation temperature and stagnation pressure, instead of using static temperature and static pressure in while making the thermodynamic analysis, because it makes the computation easier to do. Okay? So let's look at the statements. First statement, statement 1, isentropic compressor work input is always higher than the actual actual work input. Statement 2, isentropic compressor work input is always lower than actual work input. Statement 3, compression pressure ratio is higher than the expansion pressure ratio. And statement 4, compression pressure ratio is lower than the expansion pressure ratio. So which of the statements are correct here?
Second and third.
Second and third. Yeah, right. Okay. This is the correct one. So just let me briefly go over explain. So when we have compression between two pressure levels, okay, let's say just do it in terms of stagnation pressure. So when we have isentropic compression, so this will be like 1 to 2 2 prime, and when we have actual process, it will be like 1 to 2. Okay, so you can see that T2 minus T1 is higher than T2 prime minus T1 prime, T2 prime minus T1, right? And we know compressor work input is proportional to a temperature difference across the um, across the compression process. So we can see the isentropic compressor work input is lower than the actual work input. And the second statement is that because in the there will be some losses in the losses in the combustion chamber, right? So therefore the actual the pressure ratio across which the expansion process takes place in the turbine, that becomes lower than the compression pressure ratio. Okay, so the compression pressure ratio is higher than the expansion pressure ratio when we are considering real Brayton cycle. Okay, this is because there is a pressure loss in the combustion chamber. Okay, so now from now on, if we start doing problems on real Brayton cycle, we have to we should know that the compressor pressure ratio and the turbine pressure ratio need not be equal. Okay, okay, all right. Okay, so let's move on. Question 3, this is pretty straightforward. Polytropic efficiency of turbine is defined as the ratio of ideal work output to polytropic work output, polytropic work output to ideal work output, polytropic work input to ideal work input, ideal work output to polytropic work input. So which is the correct option here?
Option A.
Just think over it. So let's say let's draw the, so I say efficiency should always be lesser than 1, right? So if we dot again TS diagram, okay, so now let's say this is our P03 and P04, two pressure levels. So when we have isentropic process, this is like this. Ideal work input is the like is considered the isentropic process. Okay, but the actual process is like this, which we assume as an which we approximate as as a reversible polytropic process with index n. Okay, so that's why the option is option B, because in case of turbines the ideal work output is always higher. Yeah, ideal work output is always larger than the actual work output. Okay, so it has to be polytropic work output divided by the ideal work output. Okay, all right. So this is ideal and this is our actual thing, but we are approximating it as a polytropic reversible process. Okay, okay. Now coming to question 4. um, for a given gas, the polytropic efficiency of the for a given gas and polytropic efficiency of the compressor, the isentropic efficiency of the how the isentropic efficiency of the compressor varies with increasing compression ratio. What will be the answer?
Increases.
Just think over it. Okay, let me just go back and just just derive this a bit. Okay, so what we know for the isentropic efficiency of compressor, that is, if we have P02 to P01, and this is our 01 to 02 prime, and this is our 02, this is our so isentropic, this is defined as the um, isentropic work divided by the actual work, right? This is our definition for compressor isentropic efficiency, right? So if we simplify this, we divide the numerator and numerator by Cp and Cpt01, we get this, right? So and this this T02 prime by T01, this we can represent in terms of the pressure ratio, right? So this we can write in terms of the pressure ratio. Okay, this is our formula for the compressor isentropic efficiency. Okay, this isentropic compressor efficiency. Okay, so now what we do is that we see that this compressor isentropic efficiency is dependent on pressure ratio, right? So that's why we to characterize the irreversibility, we come up with another definition for efficiency, which is called polytropic efficiency, which is independent of pressure ratio. Okay, so so in that case what we do is we approximate the actual compression process with the reversible polytropic process with the polytropic index n. Okay, so I need to add a slide here. Okay, so when we do that, so like we can assume like a polytropic process, that is like you can say PV to the power n equals to constant, which is like T equals to P to the power n minus 1 by n, right? This proportional to, this is what we get, a polytropic process, right? And you can, if you go back and look at the derivations, you will see that we define a polytropic efficiency, and the relation comes out as n minus 1 by n is equal to gamma minus 1 by gamma right. So this comes out as sorry, a second. You can go back and check the derivation which are discussed in lecture. I am not doing it again here in the interest of time, but what you get is that n minus 1 by n is equal to nc infinity in gamma by sorry, my mistake, this should be gamma minus 1 by gamma nc infinity, where nc infinity is our compressor polytropic efficiency. Okay, and now since we are approximating the actual compression process and polytropic process, this actual temperature ratio T02 by T01, this is actually the Rp whole to the power n minus 1 by n. Okay, or which we can write, this is equal to rp whole to the power gamma minus 1 by gamma nc eta. Okay, nc infinity. Okay, so and like this polytropic efficiency is defined by considering infinitesimally small changes in temperature and associated with the process. Okay, so that we can approximate that irreversible process as a reversible polytropic process. Okay, so now if we replace this ratio T02 by T1 in the expression for compressor isentropic efficiency, it comes at, so we have rp to the power gamma minus 1 by gamma minus 1 in the numerator, and in the denominator we have rp to the power gamma minus 1 by gamma into eta c infinity minus 1, right? Okay, so now the question is how it varies with the changes with the
Increasing pressure ratio.
pressure ratio, it increasing pressure ratio. So if you make the different calculation, see the plot, you will see for a constant value of given polytropic efficiency and a given gas, so when a particular gas is given means that gamma is constant, and if your eta c infinity or polytropic efficiency is given is constant, we will see that this it follows a curve like this. So on the x-axis we have eta c, the y-axis we have rp, we will see something like this. Okay, so this is our for a constant value of this thing. Okay, so now if we now increase this compressor polytropic efficiency value, so it goes like this. Okay, all right. So but one thing you can see, if you will see that if the pressure ratio is very small, then the compressor the isentropic efficiency actually approaches the value of polytropic efficiency. Okay, all right. So this is, so what we can say here from here is that as pressure ratio increases, our compressor isentropic efficiency decreases. Okay, so the correct answer is option B here. Okay, so this is for compressor. Okay, so the but if you see for turbine, the trend is reversed. Okay, so in case of turbines, the isentropic efficiency of the turbine increases with increasing pressure ratio if given a constant polytropic efficiency. Okay, all right. And go back and check the derivations again carefully, which was discussed by professor in the lectures. Okay, to or go and or read any reference to better understand the concept of polytropic efficiency. Any questions? Okay. So here I want to see mark a point here. If the this is eta c, okay, just so this is like eta c isentropic, this value. Okay, so this is eta c is this way and rp is this way. Okay, but for an rp value of 1, so if you in both of these cases, if you put rp equals to 1, you will see this basically it will boil down to this eta c is equal, like isentropic efficiency is equal to the polytropic efficiency. Okay, so yeah, so this is what I need to say. So let's move on. Now we will have some problems on stagnation conditions. Okay, so let me read out the problem. So we have an aircraft flying at a Mach number of 0.58 and the speed of sound is 330 meter per second at this altitude, and the we have to find out the stagnation temperature at the nose of the aircraft. Okay, all right. So how do we proceed with this? So how do we, let's say, how do we define stagnation temperature? So stagnation temperature is a way to incorporate the kinetic energy of the flow into it. So like the idea is, if we what will if we have a flow moving with a certain velocity, and if we just bring the flow to rest or bring it down to rest adiabatically without any heat loss, the so that the flow velocity becomes 0, what will be the temperature, right? So we can, what we do is we use energy balance, or you can say steady state steady flow energy equation to do that. So from that we define, let's say, state. So we have the, let's say, static temperature T, okay, and velocity V, right? So at state point 1 we have CPT plus half V square, right? So this is our total energy. Okay, now this is, we are bringing it to rest. Okay, so at stagnation state we only have CPT0, which is the enthalpy, and there is no velocity. Okay, so this is a stagnation state. From there we derive the revision of which problems, Subhas? Can you just today's session I didn't discuss any problem yet. This is the first problem we are doing. The question number 1 we did a derivation, that is very simple and self-explanatory. We can the question 1, first question, we just did a derivation, which is simple. If you check the PDF that we will upload later, you can understand. And and we discussed few theoretical MCQ question. This is the first numerical problem we are doing. Okay, you can look into it, like once I upload the solved PDF, and if you have any question you can ask it to me, like post it in a discussion forum or ask it later. Okay, so now if we simplify this, we get this one, V square by 2 Cp equals to T0. So from there we get the stagnation temperature is static temperature plus this 2 Cp. Okay, so this is what we can call this thing we can sometimes call is that velocity temperature, which is the temperature equivalent of velocity. Okay, so yeah, so this is the thing. And if we now simplify it, we get it in terms of Mach number, right? So if we do T0 equals to T plus V square by 2 Cp, right? So Cp is 2 Cp. So Cp is gamma, we can write Cp is basically gamma r by gamma minus 1. So if you put it there, V square by 2 gamma r into gamma minus 1. Okay, right? Now if we take a ratio by T, divide both sides by 2, we get 1 plus V square by we get gamma minus 1 by 2 V square by gamma RT. Okay, and speed of sound, which we let's say by A, that is equal to square root of gamma RT. Okay, so which means that this is like T0 by T is equal to 1 plus gamma minus 1 by 2 V square by A square. Okay, now V by A, which is the velocity of the flow divided by the local speed of sound, that is what we call is the Mach number. So this T0 by T is get 1 plus gamma minus 1 by 2 into Mach number square. Okay, so this is what we know is the formula for stagnation temperature, given the static temperature and the flow Mach number. Okay, so let's see what is given in the problem. So we have been given the Mach number of 0.58 and speed of sound is 330 meter per second, and we have to find out the stagnation temperature of the aircraft. Okay, so first we need to find, so here we need to find out T0. We are given the Mach number and the speed of sound, but what we don't know is the static temperature. Okay, so given is Mach number, which is 0.58, and speed of sound is 330 meter per second. All right, and what else was given? Right, this is what is given. Okay, and what are given is R is 287 joule per kg Kelvin, and gamma is 1.4. So how do we find static temperature from here? So the speed of sound is square root of gamma r t. Okay, right, and this is given as 330, gamma is 1.4, r is 287, and temperature is T. Okay, from here you can find out temperature. Can anyone tell me what is the temperature you get from this? What is the value of this? This is our static temperature. Okay, like what we normally know as temperature. I'll just wait for you, someone of you, to do the calculation and tell me the value of T. Okay, so what we get is 271.03 Kelvin. Okay, now we have to find out the stagnation temperature, that is T times 1 plus gamma minus 1 by 2 into Mach number square. Okay, so can anyone do this compute? Tell me. So this is like, can say 271 1 plus gamma minus 1 by 2 is 1.4 minus 1 by 2 into 0.58 whole square. Okay, just compute it and just tell me what is the stagnation temperature T0.
Two 75.24, sir.
No, do it correctly. It's not that. We have 0.58 square. Do the calculation properly. So this is, yes, we'll get 289.23 or something Kelvin. Okay, so this is the correct option, would be 289, option D. Okay, so this is clear. So now stagnation part is very important concept, because now what is done, so in all the problems of Brayton cycle analysis we have done so far, in the compressor, when we say compressor work input or turbine work output, we just used to do Cp times the temperature difference, right? In that case, the one of the assumption was that there is no the kinetic energy change is negligible. Okay, but usually that is not the case. In turbo machineries, the fluid flow velocity is quite high. Okay, so to take into account the effect of the kinetic energy change, okay, so we express the temperature and pressure in terms of stagnation, in the stagnation form, which is stagnation temperature and stagnation pressure. In that way, the stagnation temperature includes the effect of in velocity includes the effect of kinetic energy at the state point. Okay, so in and just now work done terms, earlier we used to do Cp times the temperature difference, but now we just express in as terms of Cp times the stagnation temperature difference. Okay, or total temperature difference. Okay, stagnation temperature is also referred to as total temperature in some case sometimes. Okay, all right, let's move on to the next problem. Any questions or
So,
yeah, go ahead.
so it is in a subsonic flow, no, sir. It will Mach number it will be different now. Like a m greater than 1, no, sir.
Yeah, subsonic flow Mach number is less than 1, but the stagnation condition doesn't. But the stagnation condition you can define anytime, doesn't need to be like you can define a stagnation temperature even if it's like subsonic flow or supersonic flow, because you have a Mach number. Like, yeah, so it depends on Mach number. So you will see that when the flow is really subsonic, the Mach number is very low. It's for like subsonic flows, the stagnation temperature is generally closer to the static temperature value only, so T0 will be close to T. Okay, but if it's the Mach number is greater than 1, you will see the stagnation temperature is higher. Okay, because the velocity is higher. So here, like if you go back here, is in this thing you can see that stagnation temperature depends on this velocity v square. Okay, so if velocity is Mach number is higher, means velocity is higher, so obviously the stagnation temperature will be higher in case of supersonic flows compared to subsonic flows. This is what you are asking, or something else you meant?
Yes, sir. That is, sir.
Okay, okay, yeah. So it depends on Mach number. So it can you can define a stagnation temperature anytime, whether it's subsonic or supersonic flows. Okay. All right. So next move on. Okay. So just to repeat again the idea of stagnation temperature, we idea that fluid is brought to rest adiabatically. Okay, so that's why we are seeing that so the so there are, like, if you again just do remember the steady state steady flow energy equation, we have enthalpy plus kinetic energy at the initial state. Okay, and in the final state you have just enthalpy. Okay, which we call this like the stagnation enthalpy, because and there is no kinetic energy. Okay, because the fluid is brought to rest. Okay, so based on that idea, and so adiabatically means that means there is no, in the process of bringing the fluid to rest, there is no heat loss or heat transfer involved, and there is also no work interaction. Okay, so that is the idea of defining the stagnation temperature. Okay, okay, so next is question 6. A high speed subsonic airplane is flying at a Mach number of 0.75. So here Mach number is 0.75 at sea level. The pressure at the stagnation point of the nose of the airplane is, so you have to find out the stagnation pressure. Okay, it says that the pressure at the stagnation point of the nose of the airplane. So the idea is, so if you have like the airplane is moving at a speed, which means that air is approaching at a speed like Mach number of 0.75, right? So at the nose of the aircraft, here the fluid particle will be brought to rest, right? Which means that there you have velocity is 0, and the temperature will be equal to a stagnation temperature, and pressure will be equal to the stagnation pressure. Okay, right? So that's how you go about that. So this the ratio of stagnation pressure to static pressure is related to the ratio of stagnation temperature to static temperature in this form, right? Gamma by gamma minus 1, right? This is like assuming fluid is brought to rest isentropically. Okay, because this is like the isentropic relation we are using. So if we assume that the fluid particle is brought to rest isentropically, then we can invoke this relation for stagnation pressure. So that we get P0 by P is equal to T0 by T, we know formulated in the previous question. So this is gamma minus 1 by 2 Mach number square this whole to the power gamma minus 1 by gamma. Okay, so this gives us p0 by p is equal to 1 plus, so our gamma minus 1 is gamma is 1.4 minus 1 divided by 2, Mach number is 0.75, this is 0.75 whole square, whole to the power gamma by gamma minus 1, which is 1.4 divided by 1.4 minus 1. Okay, so yeah, so if you now solve this, you should get 1.46 bar. Okay, so option A. Okay, any questions so far? So nose of the airplane, this is ours. So in any case, when we refer to something as a stagnation points, it means that the point where the flow velocity is 0. Okay, the fluid is at essentially is at rest. Okay, any questions so far? Okay, all right, let's go to the next question. Okay, so this is a question related to your polytropic efficiency. Okay, so let's go through that. Okay, so before that I will just go back and revise what I said about the polytropic efficiency, right? Okay, so okay, so we have seen that this is like the definition of our isentropic efficiency, which is isentropic work input divided by the actual work input, right? This is for compressors, and which we can simplify in this form. So in the numerator we have pressure ratio to the power gamma minus 1 by gamma minus 1, and in the denominator we have the actual temperature ratio across the compression minus 1. Okay, so now what we can do is we can see that isentropic compressor efficiency is dependent on the pressure ratio. So that's why we come up with something called polytropic efficiency, in which we assume that the actual expansion process is irreversible. We know, right? Because of the irreversibility we are getting that increase in entropy. Okay, but in case we now come up with a polytropic process, which is a reversible process, a polytropic process, to define a to explain the to model the actual compression process. Okay, and when we do that, so we can, so this is what we define the polytropic process to be, that PV to the power n equals to constant, or like T is, or like we can say temperature is proportional to P to the power n minus 1 by n, which is n is the polytropic index, and from there we can do the derivation and find out that if the polytropic efficiency is given as nc infinity, we get this relation n minus 1 by n is equal to gamma minus 1 by gamma gamma minus 1 divided by nc infinity gamma. Okay, and again the actual temperature ratio is modeled as a polytropic process, so we get rp to the power n minus 1 by n. Okay, which is again we can express in terms of polytropic efficiency. Okay, and finally we get this expression, right? So this is how isentropic compressor efficiency depends on pressure ratio rp and polytropic compressor efficiency nc infinity. Okay, and we get this plot when pressure ratio increases at a given value of polytropic efficiency, the compressor isentropic efficiency decreases. Okay, so the question was, for a given gas means gamma is constant, and a polytropic efficiency of the compressor. So we are given a value of polytropic efficiency and value of gamma. In that case, the isentropic efficiency decreases with increasing compressor ratio. Okay, for turbine it is opposite. You will see, if you look at the derivation, you will see for turbines, when the pressure ratio increases, that for a given value of polytropic efficiency, the turbine isentropic efficiency actually increases. It is, the trend is reverse for what we see in case of compressors. Okay, these are the formula that we'll put to use in this problem. So let's go through this problem. So we have a multi-stage axial flow compressor, which means that the compression is happening in different stages. Okay, we have mass flow rate of 50 kg per second. So we have m dot air is 50 kg per second given. Total pressure ratio of is 35. Okay, so the total pressure ratio is 35, means that the compression is happening in different stages. That's why we are able to achieve such a high pressure ratio. So rp is 35. Okay, the compressor has a polytropic efficiency of 0.9. so eta c infinity is 0.9. Okay, the inlet flow condition is described by T01. So now again, from now on, whenever we are dealing with real cycles, instead of static temperature and static pressure, we will be using stagnation temperature and stagnation pressure, but the process followed for the evaluation of different quantities stays similar. Just we are using stagnation quantities in terms of static quantities. Okay, rest of the process remains similar. So here we are given T01. This is the inlet to the compressor, that is 288 Kelvin, and the inlet pressure is 100 kilopascal. Okay, so assume the flow in the compressor is adiabatic, which means there is no heat loss, which is generally the assumption. We have the constant gas properties throughout the compressor. Gamma is 1.4 and Cp is 1004 joule per kg Kelvin. Okay, the first question is, you have to find out the exit total temperature. Okay, total, as I said, total temperature, total means stagnation only. Okay, so you have to find out stagnation temperature at the exit of the compressor. Okay, so part A. So let's say if I draw the schematic of the compressor, so inlet is our T01 and outlet is T02. Okay, so T02 divided by T01. Okay, so now again this is like an non-isentropic process, but we can express this in terms of pressure ratio as n minus 1 by n, right? So this is what, rp to the power gamma minus 1 by eta c infinity gamma. Okay, so this is like 35 whole to the power 1.4 minus 1 divided by 0.9 into 1.4. Okay, so can anyone compute and tell me what is the value? So this is like T02 will be equal to, T01 is 288 times, let me make a quick calculation. So this is 0.4 divided by 0.9 divided by 1.4. Okay, so this is like 35 to the power 0.31746. Okay, so now if you solve this, you will get T02, which is the temperature at the exit of the compressor, is so this will turn out as about 890.4 Kelvin. Okay, right? So now what we see is the ease of when we are defining the polytropic efficiency, we can directly write we can directly find the temperature at the end of compression process using pressure ratio. Okay, usually we can do that when it's isentropic process, like we write the temperature ratio is equal to pressure ratio whole to the power gamma minus 1 by gamma. Okay, but now we are getting and then use the definition of isentropic efficiency to compute the final temperature. Okay, but now with the definition of with polytropic efficiency, we can directly find the temperature ratio. We can directly express the temperature ratio as a function of pressure ratio whole to the power this factor, which is okay. So now we can see if the polytropic efficiency is basically 1, which means that the process becomes isentropic. Okay, because now this becomes 1, the temperature ratio will be equal to rp to the power gamma minus 1 by gamma, which is essentially isentropic, the expression for an isentropic compression process. Okay, so the first part is done. Let's do the second part. The second part, we have to compute the compressor adiabatic efficiency, which means the compressor isentropic efficiency. Okay, this means that we have to find out compressor isentropic efficiency, which is eta c. Okay, so we had a formula for that. So eta c is equal to rp to the power gamma minus 1 by gamma minus 1 divided by T02 by T01 minus 1, or rp to the power gamma minus 1 by gamma minus 1 divided by rp to the power gamma minus 1 by eta c infinity gamma minus minus 1. Okay, alright. So if we had computed this value here, which is this rp to the power gamma minus 1 by eta c gamma, this would have come out around 3.0916. okay, so if we now put in the values, so eta c will be equal to rp is 35 whole to the power 0.4 divided by 1.4 minus 1, and this is equal to 3.0916 minus 1. Okay, so if we calculate, we will get eta c as 84.22%. okay, so what you see here is that our polytropic efficiency was 90%, but our isentropic efficiency comes out around 84.22%. okay, so now what I said, if you remember what I said while I was explaining this graph, that when you have as the pressure ratio increases, the isentropic efficiency drops, right? But when the pressure ratio is very small or close to 1, you will see the value of isentropic efficiency approaches the polytropic efficiency. Okay, like if we assume the pressure ratio is equal to 1, at that time the polytropic efficiency is equal to, we'll find that the isentropic efficiency is equal to polytropic efficiency. Okay, so like if let's say in the same the problem that we did, that was with the pressure ratio of 35. Now if you repeat the see both isentropic efficiency and polytropic efficiency are both like efficiencies which are declared for a real compression process, real compression or expansion process, but the way we are defining the efficiencies are different. Okay, so here in the when we are defining isentropic efficiency, we are just defining in terms of finite temperature differences. Okay, but when we are defining polytropic efficiency, we are assuming infinitesimally small temperature change, and then then coming out with an expression for efficiency. Okay, or in other words, you can say the actual expansion process or the real expansion or compression process is irreversible, right? So we cannot express it like on a as a process in a TS diagram. So we are modeling that process as a reversible polytropic process, okay, of with polytropic index n, all right, and then coming up with an expression for the polytropic efficiency. Okay, so you can just go over and read I think the book by Saravanan Mattu, which he said, which where the again like or go or just listen to the lectures carefully where this is derived. Okay, but both are for real processes only, but but we are defining the efficiencies in two different ways. The advantage is that in case of the polytropic efficiency, that is independent of the pressure ratio and the initial state. Okay, but the isentropic efficiency, as we see, is 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 depends on the pressure ratio and also on the initial state of the initial state inlet state of the compressor. Okay, while the polytropic efficiency is independent of that. Okay, so that is the advantage of using defining a polytropic efficiency. Okay, because that doesn't depend on the pressure ratio. Okay, all right. Okay, so the last part, 7c, we have to calculate the compressor shaft power in megawatt, which means that the compressor work input shaft power. Okay, so we can find out the specific compressor work, which is equal to now, which is small wc, which is equal to cp times T02 minus T01. Okay, so note here we are now approximating a real cycle, so which means that our we will deal with stagnation temperature. This is 1004. Okay, not just in this problem it's set at 1004, not the standard value 1005. Okay, so T02 is 890.4 minus 288. Okay, so this you will get 890.4 minus 288 into 1004. This will come out as 6.04 point, sorry, 604.8 kilojoule per kg. Okay, now to calculate compressor power, this will be like mass flow rate of air times the specific compressor work. Okay, so this is in kg, mass flow rate is in kg per second, so the output will be in terms of joule per second, which is in the joule per second is watt, right? So this is m dot a of mass flow rate of air is given as 50, so this is 50 kg per second into 604.8 kilojoule per kg. So this will get 604.8 into 50. This comes out as 30240.48 kilojoule per second. Kilojoule per second is kilowatt, but we want the answer in watt. Okay, sorry, we have the answer is asked in megawatt, so we have to again divide it by 1000. Sorry, so this is part C of the problem. So this is 30.24 megawatt. This is our compressor power. Okay, so always make sure when we are solving this question, be careful of the units, what is exactly asked. So if it's like specific work, it should be in kilojoule per kg. When it says power, means the unit is watt, and in that case we have to multiply it with the flow rate of air to compute the total power. Yes, it is the power required. Obviously, it is the power required. This is like, this is what we can say is the power required to run the compressor, or you can say shaft power required to run the compressor. Okay, and this we have seen that this shaft power is basically provided by the turbine. Okay, the turbine work output, a part of the turbine work output goes into running the compressor, right? Okay, so I guess all this is clear, right? This problem on compressor related to polytropic efficiency. Okay, and move on to the next question. This is on combustors. Okay, so let's see. it says that we have a gas turbine combustor, so we are just focusing on the combustion chamber here. It has the inlet condition of, so let's see, we have a combustion chamber, so we have an inlet condition is 02 and outlet condition is 03. Okay, so it says that inlet condition T02 is 800 Kelvin, pressure P02 is 2 megapascal, which is 2 into 10 to the power 6 pascal. The mass flow rate of air m dot a is 50 kg per second. Okay, and then it says that then a hydrocarbon fuel with ideal heating value QR, which is, we know this is the calorific value, which is 42,000 kilojoule per kg, is injected into the combustor at a rate of 1 kg per second. Okay, so this is like the mass flow rate of fuel. Mass flow rate is at which the fuel is supplied, that is 1 kg per second. Okay, so okay. Now then it says this, that is one thing is the burner efficiency, eta B is 0.995. The total pressure at the exit of the compressor is 96% of the total inlet total pressure, which means combustion causes a 4% loss in total pressure. Okay, so again, like this combustion chamber, we are saying this is a combustion chamber for real gas turbine based power plant or real Brayton cycle. So as we have seen, in ideal Brayton cycle we considered the heat addition process in a combustion chamber is at isobaric, which means happens at constant pressure, but in real case there is a pressure loss, and the pressure loss is says that there is a 4% pressure loss. Okay, and now we have to find out the following. We have to first find out the fuel to air ratio. Okay, so this is pretty straightforward. The fuel to air ratio F is like m dot F divided by m dot A. So this is 1 by 50 basically. So this is 0.02. Okay, so this is our fuel to air ratio. Okay, next question is, we have been asked out to find out the combustor exit total temperature in Kelvin and pressure in megapascal. Okay, so now one thing is there. So we have the combustion chamber, let's say combustion chamber. Okay, so here we have mass flow rate of air coming in, all right, and also we are feeding in fuel. Okay, so the total mass flow rate that is coming out is m dot A plus m dot F. All right, this is important because in again remember, in case of an ideal cycle we assume that the mass flow rate of the working fluid is constant in all the components. Okay, but in reality we are adding some additional fuel. We are adding fuel in the combustion chamber for combustion to happen, right? So the mass flow rate of the mass flow rate of the working fluid that is coming out of the combustion chamber is actually m dot air plus the mass flow rate of fuel. Okay, so yeah, Rama, what you have a question, you can unmute and ask. Okay, yeah, so the mass flow, so the mass flow rate that goes through the turbine is actually the mass flow rate of air plus the mass flow rate of fuel. Okay, and the working fluid is also not air there, which is like exhaust gases. Okay, so yeah, if we want to find out the, so this is at temperature T02, we need to find out the temperature T03. Okay, so what we need to do is like simple energy balance. Okay, so what is the energy or enthalpy of the fluid that is coming in, which is m dot A times 802. This is the enthalpy of air that is coming in, right? Mass flow rate of air times the in stagnation enthalpy. Again, we are, if we are saying stagnation enthalpy, which means we are already considering the kinetic energy along with this. Okay, plus we have the mass flow rate of fuel, right? times our QR. QR is our fuel calorific value. Alright, so we are supplying some amount of fuel. So if you remember, so the burning of fuel supplies some energy. So we are burning m dot f amount of fuel, so that releases an energy of m dot f times QR. Okay, all right. And in the outlet of the combustion chamber, we have mass flow rate of air plus mass flow rate of fuel times the enthalpy of first the stagnation enthalpy at the exit. Okay, so this is the energy balance. Now one more term that comes in is our, which is called eta B. This is what we call combustion or burner efficiency. So like we are to understand it is, so we are supplying a m dot f amount of fuel. Okay, and that the fuel calorific value is QR. So the input fuel energy is m dot f times QR. Okay, so the idea is the if we are burning m dot f amount of fuel, m dot f times QR, this is the amount, this is the rate at which we will get the energy from the combustion. Okay, but in actually there are some heat losses, incomplete combustion, and all those things. So there is some heat that gets lost. Okay, we don't get exactly m dot f times QR amount. Okay, now to account for that happens in real combustor. To account for that, we introduce this combustor or burner efficiency. Okay, which is less than 1. Okay, so like, and this shows that the total basically the total net heat input to the cycle is net heat input from the burning of fuel is actually lesser than the ideal value. So ideal value is m dot f times QR. So if you now multiply it with the combustion or burner efficiency, we get the actual heat input by the fuel burning. Okay, is this clear?
Yes, sir.
Okay, great. So now if we now divide this, okay, let me write this again. So we have m dot f 802 plus m dot f QR eta B is equal to m dot a plus m dot f times 803. Okay, so now if I divide both sides by m dot a, we get 802 plus m dot f by m dot a QR eta B is equal to 1 plus m dot f divided by m dot a into 8023, which is we get 802 is equal 802 plus, so m dot f by m dot a is fuel air ratio, f is f QR eta B is equal to 1 plus f 803. Okay, now stagnation enthalpies we can write Cp times the temperature. So this is Cp 2 times T02. Okay, so now note that at the inlet of the combustion chamber we have air, and at the outlet of the combustion chamber we have the product gases that are generated. Product gases will include what? We know that when you burn a fuel, the major gases that are produced are carbon dioxide and water vapor, right? So when we burn an hydrocarbon fuel. Okay, so when the working fluid that is entering the combustion chamber, that is air. Okay, and what is coming out is basically the exhaust gases or product gases. So in real cases we need to consider that effect because the specific heat of both the air and the exhaust gases are different. Okay, so that's why here we need to consider the different specific heat for at the inlet and the outlet. Okay, so at the inlet this is Cp2 plus FQR eta B, and at the outlet that is Cp3 times the temperature. Okay, so if you go back to the problem, we'll see that for air the Cp is given, gamma for air is 1.4 and Cp is 1004, and for the combustor the gamma is 1.33 and Cp is 1156. Okay, so we will use this. Okay, so ultimately what we need to find out is T03. So T03 will be given by, if we now divide, thus rearrange, you will find this expression. Okay, all right. So this is the final expression for T2. T0, like the temperature at the exit of the combustion chamber. So here if we now put in the values, so Cp2 is 1004, Cp3 is 1156, T02 is 800, plus F is, we computed 0.02, QR is 42 into 10 to the power 6, eta b is point, a second, let me write it with more space, matter is big. So we have 1004 divided by 1156 into 800, plus F is 0.02, QR is 442 into 10 to the power 6 joule per kg, eta b is 0.995, and this is again Cp3 is 1156, this is divided by 1 plus 0.02. Okay, so now if you compute this, let me add a slide here. Okay, so this is what it is. So this is our T03. Okay, this is our expression for T03 derived. So T03 will come out as 1390 Kelvin. Okay, so if you now use all the values or compute, so this is okay. So just made me bring it to this slide. Okay, so is the derivation process and this clear what I explained? The mainly is the how we are writing the energy balance equation here is important, and how we are incorporating the, so in the energy balance equation, the on the left side, which is the input, is like the enthalpy at which the enthalpy flux of the incoming air, which is mass flow rate of air times the stagnation enthalpy, corresponding to temperature, stagnation temperature T02. Then we have the input energy because of the burning of fuel, so which is mass flow rate of fuel times calorific value, which is the ideal heat energy, ideal thermal energy or heat input, and that we multiply it with the burner efficiency or combustor efficiency to account for the some heat losses or incomplete combustion. And at the outlet of the combustion chamber, we have the total mass flow rate, which is the mass flow rate of fuel plus mass flow rate of air times the stagnation enthalpy corresponding to that temperature. Okay, then we write the stagnation enthalpies in terms of as Cp times the stagnation temperature, and here the Cp's at both inlet and outlet will be different, because at the inlet we have air and the outlet we have exhaust gases. So with the Cp, so the Cp values are different. Okay, so we are taking into account of that here, because in real cycle this is also an important factor. Okay, so then we simplify this and put in all the values to find out T03. Okay, now to next we have to find out the, let's go back to the question. So we have found out the combustor exit total temperature. Okay, and we have to find out also the pressure. Okay, so that we say that the inlet pressure is 2 megapascal, and it says that there is a the total pressure at combustor exit is 96% of the inlet total pressure, which means that there is a 4% pressure loss. So this is our combustor exit total temperature and combustor exit total pressure P03, as it's written in the question, it is 96% of the inlet pressure, which is P02, which is 0.96 times the inlet pressure is given as 2 megapascal. So 0.96 into 2, so we'll get P03 as 1.92 megapascal. Okay, all right. Last part is clear. Any questions? So what I did in last two problems was that to show you that when we have a real cycle, like the major thing comes up in the when you have a real cycle, how we do the calculations for a compressor, and then let's say a calculation for a combustion chamber. Okay, so the major differences that we have seen till now for the real cycle analysis versus the ideal cycle. First is, in real cycle we take the temperature and pressure in terms of the stagnation values. Okay, next is we consider in ideal cases we consider the working fluid is entirely air, so we do all the calculations using the Cp and gamma values for air. But in real cycles we need to, in the working fluid is air in compressors and like in the compressor, but in the turbine the working fluid is basically the exhaust gases, which mainly contains carbon dioxide and water vapor, and we need to consider the gamma and Cp values for that to get accurately calculate the cycle parameters, like the important quantities related to the cycle. Okay, and also there are pressure losses in the we can't assume the pressure at the exit of the compressor is equal to the pressure at the inlet of the turbine, because there are pressure losses that happen in the combustion chamber. Okay, another important thing is that the mass flow rate of fuel, there is a mass flow rate of fuel in the sorry, the mass flow rate of the working fluid in the compressor is just m dot air, but the mass flow rate of the working fluid in the turbine is the mass flow rate of air plus the mass flow rate of fuel. Okay, but it generally we have seen that this fuel air ratio is generally 2% or less. So if we just use mass flow rate of air as the total mass flow rate, that doesn't incur significant errors. Okay, because fuel air ratio is, since fuel air ratio is generally less than equal to 2%, the mass flow rate of air plus mass flow rate of fuel is approximately equal to mass flow rate of air. Okay, so that's why like using mass flow rate of air for computation is a reasonable assumption, and it doesn't incur like doesn't make numerically doesn't make much difference. Okay, so is this clear? Shall we move on to the next problem? Yeah. Any doubt? Okay, all right. Now we will do a thermodynamic analysis of a real cycle. Okay, so this is the schematic of the cycle given. Okay, so we have a compressor, okay, where the air is entering at state point 1. Okay, then it leaves at state point 2 from the compressor. Then we have a combustion chamber. Okay, and it leaves at state point 3. After that we have a turbine. Okay, so this is like and then there are two turbines. Okay, you can see that the first turbine is connected to the compressor. Okay, and the other turbine, which is what we call a power turbine, that is what is providing the work output for the generator. Okay, So this is what we call is a free turbine unit. So this so the important thing here is that we see that the turbine output from the the work output from the first turbine stage is completely used to run the compressor. Okay, and the power turbine is as a separate shaft that gives a net that, and the entire output from the power turbine is connected to the generator. Okay, so is this arrangement clear what I said? So in this case the the output from the high pressure turbine or the first turbine stage will entirely go into running the compressor. Okay, and the work output from the other turbine, that is the net work output from the cycle that goes into running the generator for this for this power plant. Okay, all right. So this is the, so if you remember in the, I think in the first session, so what I discuss is like this kind of arrangement is can be used for because it has two shafts, right? This can be used for different loads like variable loads and give some flexibility, while when you have a single shaft we can use it only for like fixed loads and at fixed speed. But in case of this, when you have power turbine, separate power turbine, then this can be used for variable loads as well. Okay, so okay, let's go through the problem. So we have to find out the specific work output, specific fuel consumption and cycle efficiency of a simple gas turbine with a free power turbine. Okay, so is the schematic clear? If anyone has any doubt, just let me know now before we start the solving the problem. Okay, so let's see what is given. So compressor pressure ratio is 12. So this is our RPC. Okay, so now the pressure ratio, as is said, since we have a real cycle, we can, the pressure ratios for turbine and compressor will differ, so we can use a suffix C like that. So this is the pressure ratio for the turbine, RPC. So turbine inlet temperature is 1350, so which is actually T03, right? So T03 is our turbine inlet temperature. Okay, so now again, since it's a real cycle, we'll say that when it means that it's when we say temperature, it means stagnation or total temperature. Okay, so that is 1350. We have been given isentropic efficiency of the compressor, isentropic efficiency of the turbine, mechanical efficiency of the shaft. I will explain where this comes in the mechanical efficiency. We have been given the combustion efficiency, which is 0.99, then the actual fuel air ratio, which is F. Okay, combustion chamber pressure loss. Okay, so we generally write this as delta PCC. Okay, so delta PCC is the pressure loss that is happening within the combustion chamber. Okay, so which is 6% of the compressor delivery pressure. Okay, so what is the compressor delivery pressure? The compressor is delivering pressure at state point 2, so the pressure loss in the combustion chamber is like 0.006 times P02. This is clear what I wrote. So combustion chamber pressure loss, which I am indicating as delta PCC, that is equal to 6% of compressor delivery pressure, which means the pressure at which compressor is delivering air. So here compressor is delivering air, which is corresponding to state point 2, so the pressure is P02. Okay, so again we note that we are using stagnation pressure here. Okay, and exhaust pressure loss is 0.03 bar, which means that, so after the so some power turbine, the gases flow out through the exhaust, so in that region we are having a pressure loss of 0.03 bar. Okay, now what are the other things given? We have been given that the ambient conditions are 1 bar and 288 Kelvin, and we have been given the CP and gamma values for air, and Cp and gamma values for the combustion product gases. Okay, so again, just to remind you, the air is the working fluid in the compressor, but the working fluid in the turbines is our combustion product gases. Okay, so we need to use the values of Cp and gamma for that when we are dealing with the turbines. Okay, so anyone has any question with the problem statement, just and ask before we start solving it. Okay, all right. Okay, thank you. Okay, so what we have been given is the ambient conditions. First, let's start with. So ambient condition, pressure is 1 bar and temperature is 288 Kelvin. Okay, so now let's say in ambient conditions, what is the velocity? Let's say we have a compressor here, right? Sorry, compressor is like this. So we have the compressor here. So here it's like 1 and here is ambient. Okay, so close to the very ambient, so like it is compressor is drawing air from the ambient, and this is like a stationary gas turbine, right? So in the ambient, the flow velocity is basically 0, right? Because our um, the air in the surrounding is at rest. Okay, this is true for, because we are solving this problem for a gas turbine power plant. This won't be true when we'll do this kind of problem for an aircraft engine, which we will start taking up from the next modules. Okay, since this is air, okay, an ambient condition where the air is stationary for a gas turbine power plant. Okay, so T01 will be equal to Ta is equal to 288 Kelvin, and P01 is equal to Pa is equal to 1 bar. Is this part clear, what I wrote? Okay, so again, to repeat this, because in the ambient or the ambient condition or the air surrounding this is a stationary gas turbine power plant. This is a compressor of stationary gas turbine power plant. So ambient air is at rest, right? Okay, so this is the idea. Okay, so now what we have to find out, first we have to find out the so now we know what is the state point at the inlet of the compressor. Okay, now we have to find out what is the thing at state point 2. Okay, so now how we do this, again we can start with by the since our compressor isentropic efficiency is given, we can start with this. So this is T02 prime minus T01 by T02 minus T01. Okay, just excuse me for a minute, I will be back. Okay, Okay, so yeah, so first step is like it's the same thing that we do for all our like we have done for our thermodynamic analysis, right? So now we have to find out the temperature at the exit of the compressor, right? So this now given the compressor isentropic efficiency, so we start with the definition of compressor isentropic efficiency, right? So and then yeah, just a second, yeah, start with the compressor. So now if we now simplify this, remember we get T02 is equal to T01, T02 minus T01 is equal to T01 by eta c, T02 prime by T01 minus 1, and this we can write as by eta c. T02 prime by T01 is like the temperature ratio if the process is isentropic, so this we can write as Rp compressor to the power gamma air minus 1 by gamma air minus 1. Okay, so note that here I have specified the like I have added the subscript to gamma because now we are considering the gamma for air. Okay, so this is clear, right? This is what we generally do for to find out the temperature at the end of the compression process. Okay, so so now if we put in the values, so T02 minus T01, so first I am computing the temperature difference because temperature difference is what comes in while we will compute work done, right? So T03 by T minus T01 is equal to T01 by eta c into RPC to the power gamma air minus 1 by gamma air minus 1. Okay, so this is 288 divided by 0.86. This is the given our compressor isentropic efficiency, which is 0.86 to the power 12 whole to the power 1.4 minus 1 divided by 1.4 minus 1. Okay, so T02 minus T01, that will come out as 346.3 Kelvin. Okay, all right, and T02 will come out 346.3 plus 288, which is 288 plus 346.3, this is 634.3 Kelvin. Okay, so this is our temperature at the exit of the compressor. Okay, so this the process that we followed is we have done many similar problems on this. So given the inlet temperature, inlet conditions, inlet temperature, pressure ratio of the compressor and compressor isentropic efficiency, we are computing the compressor exit temperature. Okay, okay, so now we know if you go back here, so we now know T01. So T01 is, we know the state point T01, we know the state temperature at T02. Okay, now is the time to find out T03. Okay, so no, T03 is given, right? T03 is our turbine inlet temperature, which is 1350. Okay, so okay, so before we do that, before we compute T03, so we also need to know what is our pressure at compressor exit P02. So that will be equal to P01 times our compressor pressure ratio, right? So that is equal to 1 bar into 12, which is 12 bar. Okay, so this is our P02. Okay, so now we know the temperature and pressure at state point 1, temperature and pressure at state point 2. Okay, so next step is to find the temperature and pressure at state point 3, right? That's how, as I have said, that's how you should proceed with every problem. Okay, find the temperature and pressure at each state point. Okay, so at 1, which is we found out that is equal to our ambient conditions. Okay, 2, the temperature and pressure in set point 2, you can pressure at set point 2 is simply the inlet pressure times the pressure ratio, and the temperature at set point 2, total temperature at set point 2 is we found out by using the pressure ratio, inlet temperature, and the compressor isentropic efficiency, right? So next step is find out state point at this state point 3, which is turbine inlet or combustor exit. Okay, so here the temperature T03, which is 1100 Kelvin, this is given as the turbine inlet temperature. Okay, and next thing is the pressure P03. Okay, the pressure at combustor exit. Okay, so now if you remember, this is a real cycle. If it was an ideal cycle, the pressure at combustor exit is equal to pressure at combustor inlet, because we assume in ideal cycle it is a constant pressure heat addition. But in this case it is a real cycle, and there is, as we have seen here in the given in the problem, there is a pressure loss in the combustion chamber. Okay, which is 6% of the combustor delivery pressure. Okay, which is 0.06 P02. Okay, so P03 we can write is equal to combustor inlet pressure minus the, which is whatever is the pressure loss within the combustion chamber. Okay, so this is P02 minus, as it is given the pressure loss is 6% of the compressor delivery pressure, or 0.06 times P02. Okay, so we can write this is like 0.94 P02. So if we do that, we will get P03 is equal to 0.96 P02. So P02 is 12 bar, which is 0.96 into 12, 0.96 into 12, 11 point. So P03 is 11.52 bar. Okay, so let me again go back to the schematic. Okay, so now we know the temperature and pressure at set point 1, temperature and pressure at set point 2, temperature and pressure at set point 3. Next is temperature and pressure at set point 4. Okay, so now again to repeat this, in this case this turbine, which is, let's say, so this is our, let's say, high pressure turbine, and this is our low pressure turbine. Okay, so this high pressure turbine, the work output from the high pressure turbine should be just enough to run the compressor. Okay, and that is how this this gas turbine power plant is designed. Okay, so that's why what we need to do here is so let me write that high pressure turbine produces just sufficient work to drive the compressor. Okay, so what that means is, you have to do this is very important, and these things will come up in aircraft engines as well, because you will find that in aircraft engine also there is no net work output from the turbine. The turbine performs just sufficient work that is enough to drive the compressor, because in turbine we don't need any additional shaft power to run a generator or something. So in aircraft, when we'll start doing thermodynamic analysis of aircraft propulsion cycles, we'll see that in this case turbine produces just sufficient work to drive the compressor. Okay, so what we have to do, work matching between compressor and high pressure turbine. So what is the work input to the for the compressor? This is Cp of air, right? And note we are using the Cp of air because working fluid for compressor is air into the temperature difference T02 minus T01. Okay, all right. And now if we look at the what are the state points across the high pressure turbine, so the high pressure turbine, the work is like Cp T03 minus, here we have to use Cp gas. Okay, just note the difference in Cp here. Here we have to use Cp gas, and this is T03 minus T04. Okay, all right. Now there is one more thing. This the turbine and compressor is, this is your compressor and this is your high pressure turbine. Okay, just let me write this 01, 02, and this is 03 and 04. Okay, so now this shaft, in real cases you know that when there is a shaft there is some energy losses due to friction in the bearings and everything. Okay, so that loss due to friction is quantified by mechanical efficiency, eta mech. Okay, so the work, like the work that the turbine, there will be some losses involved. Okay, so the actual work output from the turbine has to be slightly more than what the compressor requires for the to run the, so slightly more than what is required from the compressor to compensate for the frictional losses. Okay, which we include as like what we call is the mechanical transmission efficiency. Okay, so all these efficiencies come in when we have a real cycle. Okay, so this is like, here we have to divide it by 1 by eta mech. All right, is this plot clear? So we are dividing it by, hello,
No, sir.
you want me to explain it again?
Yes, sir.
Okay, okay, okay.
Okay, just processing.
Yeah, okay. So just let me. Okay, sorry, I have to add a few slides. Just a second. Okay. Okay. So he just again. So we have compressor and we have turbine. Okay. This particular to this case. So this is like work done by the compressor and this is work done by our high pressure turbine. Okay. So now the thing is, in this case the the entire work output from the turbine has to drive the compressor. Okay, okay. So now, but when this is but these are connected by the shaft. Okay, but when there are shaft we have bearings like this and there are losses due to friction in the bearings in the shaft. Okay, so there are like mechanical losses. The shaft. Okay, so work done by high pressure turbine is should be equal to the work required by the compressor plus the mechanical losses in the shaft. All right, so actually the work output from the high pressure turbine will be has to be slightly more than what is required to drive the compressor. Okay, in that case only you can say so that the extra thing that is there, that so which is like the work done by high pressure turbine has to be greater than the work required by the compressor. Okay, excess work output goes into mechanical losses in the shaft. Okay, so this thing we quantified in terms of an efficiency which is called sorry, which we call mechanical transmission efficiency, eta mech. So this is equal to WC by WHPT. Okay, so this is valid when turbine work entirely drives the compressor. Okay, now this is clear how mechanical efficiency is defined. So that's why now we can write, so eta mech is work done by compressor by work done by high pressure turbine. So we can write work done by compressor divided by eta mechanical is equal to work done by high pressure turbine. Okay, all right, is this clear now how mechanical efficiency is coming in?
Yes, sir.
Okay, so now starting from here again I'm writing what is the work input to the compressor. This is Cp of air times T02 minus T01 divided by eta mechanical, and what is the work output from the turbine, Cp of gas into T03 minus T04. Okay, so this was 1005 T02 minus, if you remember we computed T02 minus T01 this is 346.3 Kelvin, right? Yeah, we computed the temperature difference 346.3 Kelvin, this line. Okay, so now this is 346.3 Kelvin, mechanical efficiency is 0.99. now Cp of gas is 1148 T03 minus T04. Okay, so we get T03 minus T04 as 306.2 Kelvin. Okay, so this is our temperature difference across the fast turbine or high pressure turbine. Okay, so now again what we can do is like we need to do is we need to compute the what we are trying to do is find the temperature at state point 4. Okay, so we can see that temperature and state point 4 will be 1100 minus 306.2 because our T03 was given as 1100. So this is 1100 minus 306.2, which is 793.8 Kelvin. Yeah, if you have a question, Sabaz, you can unmute and ask. You raised your hand, or you can. Sabaz, do you have any question?
Sir, T03 value is 11350. 1350.
Okay, sorry for the mistake. Yeah, thank you for pointing it out. Okay, so yeah, so I also wrote it wrong here, so this should be, yeah, thanks for pointing it out. It's 1350 Kelvin. Okay, yeah, so T03 is 1350, right? So this is 1350 minus 306.2, which is 1350 minus 306.2, which is 1043.8 Kelvin. So this is temperature at state point 4, and pressure and state point 4 we can now find out by using the definition of turbine isentropic efficiency. Okay, so turbine isentropic efficiency is our T03 minus T04 by T03 minus T04 prime. Okay, so now if we simplify this, we generally get this expression. This is one minus 1 by P04 by P03 whole to the power gamma g minus 1 by gamma g. Okay, so note here we are using the gamma for the gas here, because in turbine the specific heat ratio is for the, we have to take it for the gamma, which is 1.33. Gamma g is 1.33. Okay, so now T03 minus T02 we computed 306.2. Eta of high pressure turbine is 0.89. T03 is 1350. 1 minus 1 by P04 minus P03. This is whole to the power 1.33 minus 1 divided by 1.33. Okay, so now if we compute this, you will get P04 by P03 is equal to 3.243, and P03 is, we computed P03 is did I made some mistake here? Just second, let me go back. Okay, yeah, so here it was 0.94 P02, 0.94 P02, so this should have been, yeah, 11.28 bar. Okay, so sorry for this mistake. P03 was 11.28 bar. Okay, so P04 is P03 times 3.243, which, so we'll get P04 as 3.478 bar. Okay, all right, so let's go back to the this thing. Okay, so now we know state point 4. The last remaining is at the state point 5. Okay, so let's compute at state point 5. Okay, so now we have T04 minus T05. so this is the temperature drop across the low pressure turbine. So now we are looking at the low pressure free power turbine. Okay, so the temperature difference across that T04 minus T05 is eta of low pressure turbine times T04 into 1 minus 1 divided by P04 by P05 whole to the power gamma g minus 1 by gamma g. Alright, so this is like the what we get if we start with the definition of turbine isentropic efficiency and do the manipulation and algebraic manipulation. This is what we get, the temperature difference in terms of the inlet temperature, turbine isentropic efficiency, and the pressure ratio. Okay, so now we need to find, we know low pressure turbine isentropic efficiency, we know T04. What we need to know is the pressure ratio. Okay, so we know P04 is what we computed, P04 3.478 bar. We need to find out P05. Okay, so if we now go here, note, so now the from the turbine, from the power turbine or the low pressure turbine, from state point 5 it goes to the, it is exhausted to the ambient. Okay, ambient, and it is says that exhaust pressure loss is 0.03 bar. Okay, so from what it means that from 5 to when the gases are exhausted into the ambient pressure, into the ambient or the surroundings, in that there is a pressure loss of 0.03 bar. Okay, all right. So which means that the pressure at P05 has to be higher than the ambient pressure by no, it won't be less, it will be higher. Okay, there is a pressure loss. Okay, so here there is this pressure due to exhaust, this is 0.03 bar. Okay, so which means that at ambient pressure it is 1 bar, so means that at 5 the pressure has to be 0.03 bar higher than that. Okay, so that the it's clear, right? So which is means that there is, so P05 has to be ambient plus pressure loss due to exhaust. Okay, so this is like 1 bar plus 0.03 bar, so P05 is 1.03 bar. This is clear? Okay, so like, so the pressure at 5 is 1.03 bar, and when from the 5 is the state point at the exit of the turbine, and then the gases are exhausted in the ambient condition where the pressure is 1 bar. Okay, and there is this 0.03 bar pressure loss happening in the exhaust system. Okay, so from there we can find out P04 by P05 is equal to 3.478 divided by 1.03 is equal to 3.377, right? Okay, 3.377. All right, so now we can put in the values and find out this T04 minus T05. This is equal to 0.89 times 1.43.8. This is the temperature T04 into 1 minus 1 divided by 3.377 whole to the power 1.33 minus 1 divided by 1.33. Okay, so if you solve this you will get T04 minus T05 as 243.7 Kelvin. We have to add a slide, this long problem, many concepts are involved. So all right, so what we get is now T05 is equal to T04 minus 243.7. so T04 was 1043.8 minus 243.7, so we will get T05 as 800.1 Kelvin. Okay, so now we know everything, so all the state points. Now we can find out whatever is asked for in the question. Okay, so let's check now. So we know 1, 2, 3, 4, 5 all the state points, temperature and pressure. Okay, so first is we have to find out the specific work output. Okay, so again, now important thing to note here is that the specific work output is the net work output from the entire gas turbine power plant. Okay, so here the turbine work output is already split into two parts. So one turbine is feeding the compressor, so the work, there is no net work output from that. So the net work output from the entire power plant or this cycle is the only the work output from the low pressure turbine, right? So yeah, so the specific work output is the work output from low pressure turbine only times the mechanical efficiency. Okay, because the what we are interested in the work output that we are getting at a generator end. Okay, and again the generator is connected to the low pressure turbine via shaft, right? So there are mechanical efficiencies, mechanical losses involved. Okay, so the net actual power or the work output that we are getting from the at the generator end is somewhat lesser than the work output from the power turbine. Okay, and that we get here by multiplying it with the mechanical efficiency. Okay, so this is CPG times T04 minus T05 times the mechanical efficiency. Okay, this is 1148 times 243.7 times 0.99. Okay, so this is 277 kilojoule per kg. So this is our second. Okay, so this is our specific work output. Okay, so this solves our the first part of the problem. Okay, now what is asked in the second part is the specific fuel consumption. Okay, so specific fuel consumption here is again given as or SFC. This is given as the fuel, this is given as a fuel air ratio divided by the net specific work output. Okay, so if you remember, in case of when we do aircraft performance parameter, there also we computed specific fuel consumption. There it was the mass flow rate of fuel divided by the thrust. Okay, because in case of aircraft propulsion cycle, thrust is the essential work output energy from that we are interested in. But in case of gas turbine power plant, the specific work output or the power is the output power is the energy from that we are interested in. Okay, in case of aircraft propulsion cycle is the thrust. Okay, so here it's like SFC is defined by the fuel air ratio by the net work output. So the fuel air ratio is given in the problem as 0.0204. okay, divided by 2. This is what we computed, 277. all right, this is in this is dimensionless, the fuel air ratio, and this is in kilojoule per second. Okay, we generally express it in specific fuel consumption in kilowatt per hour. Okay, so kg per kilowatt hour. So we have, if we now multiply this with 3600, we'll get this in kg per kilowatt hour. Okay, so SFC will come out as 0.265 kg per kilowatt hour. Sorry. Okay, we now got the SFC. So now the last part is our cycle efficiency. See, eta. Okay, so what is our cycle efficiency? That should be our net work output divided by the input fuel energy, right? Total sorry, it should be like Q in. So this is in specific work by specific fuel input. Okay, so now this is, if we allow it like do it this way, sorry, no, just a second. Okay, so this is like power output divided by power input, right? So here you need to consider the power output is our mass flow rate of fuel times, sorry, mass flow rate of air times our W net, right? Specific work output times the mass flow rate of air. This is our power output, and power input is our mass flow rate of fuel, okay, times the calorific value. So this is basically our W net divided by F of CV. Okay, right? So now if you put in the values, you will find that this CV is again given as the problems 4100 kilojoule per kg. So if you now put in the values, you will find the circle efficiency comes out as 0.315 or 31.5%. Okay. Okay, so this ends the problem. Okay, this was a quite a long problem, and like it has a, so what we did was a real cycle analysis. Okay, and it has many small important concepts involved. Okay, so but the major thing is that what we important part of here is that the work matching between the compressor and high pressure turbine, this was an important equation that we need to see. Okay, and like this part will come up again often when we keep doing the next set of modules, when we'll do problems on aircraft engine propulsion. Okay. Okay, so any doubts in any part of this problem, can address that.
Sir, first 1 to 5 problems, sir, for problem number 1 to 5.
1 to 5, like
1 to
question
5, 1 to 5, sir. Starting
question
from down.
starting problem. Okay, so what you want me to go through that?
Yes, sir.
Okay, just second. Okay, yeah, so first problem is basically so we had like this theoretical problem. We have to derive this condition. So we had given a reheat cycle, and we had to find out what when the specific work output will be maximum. Okay, so there is a relationship between the uh,
Second one, sir.
pressure
Second.
problem. Okay, so this is like we have 4 statements given, and we have to find out which is the correct one. So here the first statement correct is the isentropic work input is always lower than the actual work input for a compressor, and for a real cycle the compressor pressure ratio is higher than the expansion pressure ratio. It is because we have a pressure loss in the combustion chamber. Okay, the second problem. Third problem was on the definition of polytropic efficiency. This is also simple. Question 4 was when we have a given gas and polytropic efficiency of the compressor, what happens to the isentropic efficiency. This I discussed once again, but this like how the pressure ratio, so isentropic efficiency depends on the pressure ratio, while we define polytropic efficiency so that it is independent of the pressure ratio and the compressor inlet conditions. Okay, so from there, from the
Okay, sir.
derivation, we can get an expression for relating the compressor isentropic compression ratio and the polytropic compressor isentropic compressor efficiency and polytropic compressor efficiency, and we have seen that with increasing pressure ratio the isentropic compressor efficiency decreases. Okay, and question 5 was again on we did find out the stagnation temperature just by applying the formula. So once you know the static temperature and the Mach number of the flow, you can directly find the stagnation temperature from this relation. Okay, so yeah. Okay, anything else?
Sir, fifth one, sir.